Let's revisit the Chapter 8 LED toggle example. Recall that in this example what we did is that we moved the debounce delay to the end of the loop, and that basically what we're doing is we're continually looping through here, sampling the switch every 15 milliseconds, which is equal to this debounce delay macro. Well, now that we know how to do periodic timer interrupts, why don't we use a periodic timer interrupt to do this delay sampling instead of putting this software delay directly in our loop? So what changes do we have to make to our LED toggle example? Well, first we're going to have to add a ISR, and here we're going to be using timer 3 to do this sampling. We chose timer 3 in this example instead of timer 2 simply to illustrate that it is available. And what we're going to do in here is that inside the ISR, which is going to be called every 15 milliseconds, we're going to read our switch value. Recall that our switch here is actually on RB13, and we're going to store that in a variable here, U8 underscore value switch 1, and that's going to contain the state of the switch. Before we exit the ISR, we're going to clear our timer 3 interrupt flag. What we're going to so we've made this change, and now we're going to say that switch 1, which used to be equal to this, is now going to be equal to the value of this variable. These other switch macros, switch 1 press, switch 1 release, has not changed. Let's look at the declaration of this variable here. It's an unsigned 8-bit variable, but we're also using the keyword volatile. It's very important that if you have any variables that are used inside ISRs to declare them as volatile, this will disable certain compiler optimizations that could make compiled code operate incorrectly. Basically what this means is volatile means that this variable can be changed in background code instead of only being changed in foreground code, and that all that does is simply disable certain compiler optimizations. So if you write a variable in an ISR, be sure that you declare it to be volatile. This shows the timer 3 configuration code. Note that it looks almost identical to the timer 2 code, except we replaced T2 with T3, and we're writing PR3. There is one additional line, this line right here, in which we're setting the T32 bit of the T2 configuration bit register to a 0 to ensure that timer 2 and timer 3 are configured as two separate 16-bit timers. The only other change that we had to make to the LED toggle code was that recall that at the bottom of this loop we had this delay for 15 milliseconds down here to debounce it. Well, that is no longer needed. We've removed it from here. It's no longer here because now what's happening is the hardware timer and the interrupt servicing for the timer is sampling the loop. So what's going on now is that this loop is simply circling through here very fast, and it's simply sampling that variable that's being set by the ISR every time through the loop. Recall that Chapter 8 also had a more complex problem involving two switches. You could use the exact same approach of using a timer ISR to sample these switches, except now you would need two variables. One variable for storing the result of switch 1 and another variable for storing the result of switch 2. You'd also have to change the macros for switch 1 and switch 2 appropriately, just like we did in the LED toggle example. We'll encourage you to use the ISR approach of sampling mechanical switches as it is a very efficient way of doing that. And now what we're going to do is we're going to show you a couple of additional approaches for solving this problem using switch sampling. These approaches are simply shown as alternative methods. We're not advertising or advocating that these are the best approaches. As always, there are multiple ways to solve any particular problem, and here we're simply showing you alternative methods for solving this problem. So the first alternative solution that we're going to use is going to put more work of our previous solution into the ISR. That additional work will not take that long to execute. Remember, a golden rule is that you do not want an ISR to execute for very long, but there will be more code in an ISR than just sampling the state of a switch. So what we're going to do is we note here, before we used two states to implement this when we were waiting for a press and release, what we're now going to do is we're going to implement what's called a semaphore in our ISR, which is simply a fancy name for a variable that's going to be set by a background task and read by a foreground task. And what we're going to do is we're going to set a semaphore that indicates when a complete press and release of a switch has been done. What we're going to see what that would allow us to do is it will allow us in our foreground code, our main code, to only use one state for this press and release instead of two states. That will make our code in our main, our foreground code, simpler while making our code in our ISR more complex. So here's our new code for our ISR. It's still doing this where it's sampling the switch and placing it in a variable. It's also clearing the interrupt flag, but now we've added this code right here, which is implementing a small finite state machine. The job of this small finite state machine is to set this variable here to a 1 whenever we've experienced a complete press and release. Well, how does it do that? Well, there are two states in this finite state machine. There's wait for press and wait for release, and this is going to be the state variable that it's going to use, and it's initially set equal to wait for press. So whenever we come in here and we're sampling the switch, if the switch is pressed and our variable, we're going to call this a semaphore, is 0, what we want to do is we want to go ahead and progress to wait for release. So we'll go ahead and exit the ISR. 15 milliseconds later, we'll come back in here, and now we'll be in state wait for release. If the switch is indeed released, then we'll set our state back to wait for press. But more importantly, we're going to set our press and release semaphore here to a 1, indicating that, hey, we have seen a complete press and release of the switch. Now, what we're relying on is that the main code is going to be watching this variable, and when it sees that it's a 1, it will go ahead and clear it to a 0. Note that this code here never clears us to a 0, where it only sets it to a 1. We're checking this semaphore here to be a 0 to make sure that the main code has consumed our previous semaphore. This is sort of optional. We really don't have to do that. We could eliminate this, and all that would mean is that we'd be resetting this variable multiple times if we had multiple presses and release without the main code actually clearing this variable. So in our main code, we now have state wait for press and release 1, and what we're doing is we're waiting for that semaphore to be set to a 1, indicating that we've had a complete press and release. Once it's been set to a 1, we'll clear it to a 0, and then we'll go to this state right here, state wait for press and release 2. When we're in this state, we're gonna, we need to make sure that our LED is on, and now we're going to wait again for a complete press and release. Once it's been press and release, we'll clear it again, and this time we're going to check our, we'll go and do the rest of our code as we did in the previous solution, where we'll check to see if switch 2 is a 1. If it is, we'll start blinking the LED, else if it's a 0, we'll go back to our original state here. So the key thing here is that now, where we used to have 4 states here, we now only have 2 states, because this semaphore right here is detecting a complete press and release of the switch. Yet another approach would be to simply take our entire finite state machine and put that in the ISR. There is one problem, however. Recall that we use a software delay to blink the LED, and yet we don't want to put software delays inside ISRs. So what we would do instead is we would declare a semaphore, another variable called doBlink, that when we wish to blink the LED, we would set it to a 1. Now, what we would do in our main code, since we moved our entire finite state machine up to here, the only thing left for this main code to do is to simply print out the debug message for the new state, and then check this doBlink semaphore. If it's a 1, then what we would do is we would blink the LED. We'd like to point out that even though you can do it this way, probably the simplest way and the cleanest way is to simply use this approach back here that we did for LED toggle, in which the only thing that the ISR does is sample the value of the switch and start off on a variable, which is then going to be checked by the foreground code, that is the main code. So you've seen that there are usually multiple ways to divide the work between the ISR, the background code, and main, the foreground code. The right choice is the one that services the I/O event in a timely manner, and there can be more than one right choice. So some golden rules to remember. The ISR should do its work as fast as possible. Do not put long software delays into an ISR. Really, you should try to avoid all software delays, but sometimes you might need some short ones. An ISR should never wait for I/O. The I/O event should either trigger the ISR, or the ISR should just sample the input, as in a periodic timer interrupt service routine. And finally, an ISR is never called as a subroutine.